So you were too kind, but you know, this talk starts at the end of a very long day and a very intensive program. Yeah? So it will be very difficult to do something which will be of interest for all of you, and I will try to do my best to do this. The first thing I thought when I knew that I had to speak at the end of a day was to clean up all what I will say from heavy mathematics. And hopefully I succeeded in giving you the feeling of how nice can be this problem, of how few let's say, how few I did on closing problems and how many problems remain open. Yeah. So the talk is connected with, let's say, a toy model, or maybe it would be correct to say more than one toy model, which are intended to mimic the relaxation of a gas towards the Bose-Einstein distribution. This is a very old problem. There are many models that are able to capture this behavior, but unlikely there is not too much mathematics, which gives you the rigorous feeling of what happens. Yeah? So I will split my talk more or less in three parts. The first part is devoted to a model which was introduced first by two Italian physicists in the 90s, Kaniadakis and Quarati. They were working at the Polytechnic of Turin at that time, and they have this idea to derive in a phenomenological way this type of equation. And then this is part of, let's say, a general modeling about Fokker-Planck models, and more or less Fokker-Planck models with superlinear drift. Yeah? As you will see, the equation is very particular. Yeah? We are used to see Fokker-Planck model in which is the diffusion which is nonlinear, but the confinement is linear. Yeah? Here the physics suggests that the diffusion is linear, but the drift is nonlinear. So it's completely different from what we are used to see. And this will lead to something that I did recently. Let's say you can prove something about this model. So for example, as always, when I speak about Bose-Einstein distribution, I will be more precise later on. There is some sort of critical mass, like in the Keller-Segel model. We saw many times this property. If you are below, you can hope that the gas for the rest of the time will remain regular. If you are above a certain critical mass, then you will look condensation. And this is a very important phenomenon to be able to follow. And then last, I will speak about some recent works I did with colleagues in Pavia, in which we observed the same phenomenon, let's say condensation, but simply means that the steady states of this equation have some part which is singular. Instead of looking at linear diffusion and superlinear drift, since we were not able to obtain a complete mathematical picture, we moved to a topic that was maybe easier. So we studied sublinear diffusion with a linear drift. This type of equation gives you the same sort of steady states, but it's simpler. Since you can apply to them well-known established theory of mass transportation, Wasserstein, so you have a nice mathematics that can you do with this equation. But I outlined this. This is something which is nice from a mathematical point of view, but it's not the real physical problem. The real physical problem is the first one. So this is what I write down, and unlikely I started to think to this type of problem when I was visiting the University of Toulouse for a month of visiting professor. They started with Naufel, which is no more with us, and this is really a bad news, but you know it happened. And so part of what, let's say, that this talk is in memory of Naufel. Yeah. There are many, let's say, many studies on this. The first one, more or less, will be the content of the first part of this talk. Then we were interested with Naufel and Irene Gamba on a problem which is directly related with the fact that you have Bose-Einstein distribution, and so the possibility to have some part of distribution which is condensed. And so we study in general the problem of minimizing sublinear entropies when you have a constraint of mass, of both mass and energy. Surprisingly enough, this is a problem that goes back to Bose-Einstein distribution, but it has been touched in a rigorous way only recently. If I remember well, the first paper has been written by Escobedo and Michler in 2003 until 2004, if I remember well. Yeah. And then the third research has been done with co-workers in Pavia, with Giuseppe Savarese, Stefano Lisini, and Simona Fornaro, which is directly related with a problem like this, in which you have a steady state which can have singularities. And the last one, you know, I have the impression that it will remain a research that has to be done, since Naufel is no more with us. This is the model. This is Kaniadakis-Quarati model. It looks very simple. Yeah? You know, there is, this is written in divergence form, there is a linear diffusion, and then the drift is nonlinear. There is this part in red which is added. And this is due to, they found this in a phenomenological way. There is a correction to the drift term in the Fokker-Planck equation, which is due to the presence of quantum indistinguished particles. Yeah? So depending of the fact that you have bosons or fermions, then you can here you can set delta equal to 1 or delta equal to 1, 1. There are two completely different problems. By the way, if like the usual linear Fokker-Planck equation can be taught as the grazing collision limit of the linear Boltzmann equation, let's say of the Boltzmann equation of particles which relax in a host medium, let's say in a background, this equation can be derived within the same mathematical structure, let's say, with this grazing collision limit, thinking to bosons which are relaxing into a background. Can be so. This is a private communication that Naufel did to me the first time that we started to speak about this problem. Yeah? I think that it is not published, but you can easily obtain this result. So the peculiarity of this equation is exactly in this nonlinearity. Yeah? And if you are looking to the steady state, so clearly, as always, you are looking for a related entropy, and then you check immediately that if you take h of f, like the difference between the usual Boltzmann entropy and the Boltzmann entropy evaluated in 1 plus f, and then you add, as usual, the energy, then what you can see is that this is an entropy for the Fokker-Planck equation. It works. And it has this peculiarity, which is sublinear. So the growth, if you have only the Boltzmann part, this is a little more than linear. But if you subtract this piece, then you are sublinear. And there is maybe the first study was done by Demengel and Temam. There is a nice property of sublinear functionals that they don't see singularities. If you evaluate this function in a Dirac delta, then it does not appear. Yeah? It's funny. And clearly, it does not hold only for this functional, which is related to Bose-Einstein entropy. It works for all functions which are sublinear, that satisfy a simple property of sublinearity. Yeah? Now, if you take, in the class of all functions which have the same mass, then the Bose-Einstein density, which I wrote here, is the minimizer of this. This is fairly standard. Yeah? What is not so standard is that if you want to obtain, you know, here there is v squared plus lambda, then lambda is bigger or equal than 0. Let's say if you put inside here the Bose-Einstein density, and you are looking for the density which has the maximal mass, clearly the maximal mass is obtained when lambda is equal to 0. But this integral in dimension 3 is bounded. For the simple, if you pass to spherical coordinates, then you have exactly that in 0 there is no blow up. So this is a bounded quantity. This bounded quantity is the maximal amount of mass that then I can put with a regular function in this entropy to find the minimizer. So the problem that naturally arises is what happens if I start with a mass which is bigger than the critical mass. This is a very good problem, so Einstein suggested that maybe there is some condensed part which is set in 0. And when he said this, so deltas were not known. This is, So there is a huge literature, not clearly on this Fokker-Planck equation, but at least on Boltzmann equation. Boltzmann equation for Bose-Einstein particle is very difficult. The operator, the collision operator is of order 4, and there are, from the mathematical point of view, a series of results which are due to you. In any case, in which he was able to prove something for some particular kernel, but not too much. And then there is another model which is well studied, the Boltzmann-Nordheim kinetic equation, more or less is 1D. And concerning this equation, there is a recent result. There is a long, huge number of references on this. I discovered that there is also a journal, which is low temperature physics, in which, any year there are 20 papers published on this Bose-Einstein condensation stuff. But there is an interesting paper by Herbert Spohn in Physica, in which, concerning with the Boltzmann-Nordheim kinetic equation, is trying to follow the condensation, doing an assumption and finding an equation satisfied by the condensed part. Some part is rigorous, some part no, but in any case it's interesting. Unlikely this cannot be applied to this Fokker-Planck equation. It's very difficult to follow what happens after the blow-up. And then I put here a lot of papers which are devoted to numerical methods, and starting with Bouet-Cordier, and then also Peter Markovich and Lorenzo Pareti studied this with Bau years ago. And then I tried to prove something, to see if there is a possibility to derive this Fokker-Planck equation from the full Boltzmann equation, at least in dimension 1. And so we got some results starting from some sort of caricature of Katz's model with a collision integral of order 4, and this is something that still has to be published here. So, few results on this equation. The first result is devoted to fermions. Let's say the case in which delta is equal to -1. Here there is no blow-up. It's a completely different problem. And they succeeded in proving a lot of properties, including global existence, but the local existence theorem holds also for this equation. So I will start from the fact that at least locally I know that this is an equation for which there is a solution. And then there is also a paper of 2 years ago in which the model for bosons is studied in dimension 1 of the velocity variable. But in dimension 1, you don't have formation of singularity. You have no critical mass. So in a sense, so the problem is easier. You start with a regular initial datum. This remains regular for all time. So it's not exactly what one wants to know. In the physical space, I know that the steady state has, at the end, I know that it has to be, when I am above the critical mass, it has to be a singular part. So the idea was, how can I understand if this condensate is formed after at time 0 plus, if it is formed after 1 second, after 1 hour, or when time goes to infinity. This is what, and if you are looking to numerics, even if there are really good papers on numerics, it's very difficult to say that this numerics is conclusive, since to mimic a delta with numerics is always a problem. You see that your method is blowing up, but you don't know exactly if it's blowing up since there is condensation or the. So it's not clear, at least. So at least this toy model seemed to be a good model to check something. Yeah? There is another model which is Companet's equation. Here, Companet's equation is written in terms of the momentum coordinate, and as you see here, you can easily derive that the steady state is the Bose-Einstein distribution with a to the power p, which looks instead. And this has been studied. This can be derived. There is a lot of huge, also here, huge number of references to this, and I put only 2 references to let's say 2 people, which is here. Okay. Both is Escobedo. No, maybe Herrero is not here. Velasquez is here. But it's not Kaniadakis-Quarati model. If you write Kaniadakis-Quarati model in terms of the momentum coordinates, it has different exponent here and different exponent here. Yeah? So it's a different equation. And then, since it was, or at least it appeared like a difficult task to follow the solution for the Kaniadakis-Quarati model, we thought to, let's say, an easy problem. The fact is that if you think to Kaniadakis-Quarati model in 1D, then still is a difficult problem to do when the nonlinearity is high. It's different when you have the nonlinearity in diffusion, and so, for example, you have a linear drift. And this gave the idea to study exactly this sublinear diffusion problem. And here, the diffusion, the picture in Kaniadakis-Quarati model is that you have linear diffusion, so you take something, the diffusion spreads out the solution, and then there is let's say a confinement, which is nonlinear, that shrinks the solution. And at the end, if the mass is too big, the nonlinear confinement will win. Yeah? So you can think to the problem in a different way. So there is some diffusion, but it's not so good. Let's say there is a bound from above. Even if R is big, I cannot cross a certain value. So when the solution starts to increase, the diffusion is no more acting. And so the linear drift wins. So at the end, I have always steady states with I can have at the end always steady state with a singular path. Here there are the properties on the sublinear diffusion beta that allow the formation of steady state with singular path. The typical case I set here is that when the function beta is a function of this type when n is bigger than 2. This is enough to produce a steady state with singular path. We checked it in the pertinent literature, but we asked it also to Vasquez, but no one apparently was studying this type of diffusion. It's an interesting one, since you can start with a measure, let's say with a lot of deltas which are localized somewhere, and then you can follow what happens. Yeah? Last, this was the starting point of our research, is a model in which we try to generalize this idea of Kaniadakis and Quarati, setting what we call superlinear drift. So if you put instead of f a function which is integrable, let's say the linear function, let's say the linear drift is exactly at the border, so it gives you a logarithmic growth. As soon as you put here rho times rho to 1 plus delta for any delta small, then this is bounded, and so you have still this phenomenon in which the drift is acting very strongly. And the idea was that you can produce condensation still in dimension 1, which is not the case for the usual Fokker-Planck equation with d of f equal f times 1 plus f. Yeah? It's exactly what is written here. If you take, so for example, the drift d of n of rho equal rho times 1 plus rho to the power n. In the usual Kaniadakis-Quarati model, this is 1 plus rho. It gives you the Bose-Einstein distribution. Then you set n bigger than 2. Then the steady state, as you see, there is n here, but 1 over n here. So when you take lambda equals 0, if n is bigger than 2, this function is integrable, so you have the phenomenon of the critical mass still in dimension 1. And so, honestly, we thought, take a 1D model, try to study this 1D model, since usually 1D models are easy to check. Maybe we succeed, but it was not the case. It's a terrible model from a mathematical point of view, still in dimension 1. Yeah? Let us check why. So let us use the local existence theorem by José Antonio Lorenzoni and Rosado, and let us consider in any dimension the Kaniadakis-Quarati model. And then you perform a simple computation. Let's say, what happens to the L2 norm? One can say, this is misleading. This is misleading since, for example, if I take another power, so if I take the integral of f log f, something different happens. It's not so. You can check, but the behavior more or less remains the same. You have always this problem. Then, like in the Fokker-Planck equation, you get the gradient square with the minus sign, and here instead of this term is added. If you have only this, then it's easy, since you can control with the gradient square by Nash inequality, you can control the L2 norm. And here you have the L3 norm, L cube norm. This makes the difference. So in a way, to control that the L2 norm is not blowing up, what you have to do is to control the f cube in terms of the L2 norm of the gradient. Now one uses standard Nash type inequality. I said there is a general one we derived more or less 10 years ago. Of course, there are plenty of them. And then there are exponents here, which depends on the dimension and on the power. P prime and P are the conjugate exponents. And if you set what you are looking for, so for example, P prime is equal 3, and then the dimension is equal 3, then you immediately conclude that this inequality, which relates L1, the gradient in L2 to the square and L cube, cannot be used. Since to control the norm to the cube, you need 6 over 5, which is bigger than 1. So there is no way to prove this. Clearly, for the linear Fokker-Planck equation, you have. And so for the linear Fokker-Planck equation, any solution remains regular, the L2 norm can be controlled, and you have also a maximum, which is, this is an old idea of Nash to do this. Yeah. Now I try to use another inequality in which instead of having only L1 and the gradient, I put L1, L2, and the gradient. I don't say, but it's a usual interpolation inequality. By using standard trick like Nash, you can derive this, and this can be used. So if I mix L1, L2, and the gradient of L2, then I can control L3. And here are the exponent, and then the exponent now is equal to 1. So I can control L3 by means of L2, L1, and the gradient in L2. Here the exponent is equal to 1. If I use this new Nash inequality, what happens? It happens that, as always, this was the standard term, then the term L cube is this one in red, and so since the exponent here is the same exponent like here, I can set, in terms of the gradient, which is negative, I can set a part which is 1 minus 1/3. And as you see, you have a price to pay. You can do this, but then the price that you pay is that you have to take the mass, which is strictly less than 1, to control the growth. So in a sense, what you get is some sort of smallness assumption to have regularity. So you have to fix the mass to be strictly less than 1 to control the growth of the L2 norm. But this was expected. Yeah? And this is the condition. You set the mass small and the L2 norm small in such a way that you have this quantity which is less or equal than 1. And then you use the usual Nash inequality. And if you do this, and this is the more difficult mathematics that we present you today, we all are tired, so it's better to not insist on this. Sorry. Then what you do is that you obtain a differential inequality in which only the L2 norm is involved through the smallness of this, the smallness of the mass. And it's not difficult to conclude this is a differential inequality. You have something inside that you want to control that I call epsilon way of t, and if you have this constraint that the mass is so small that you can control, then if you take m small enough in such a way that the solution to this equation is equal to 0, then you cannot increase more, and then you remain below this value for all time. So paying a price, this shows that the Kaniadakis-Quarati model, let's say the price that you have to pay, you have to stay below the critical mass, but it's very difficult to quantify, but at least if you take the mass sufficiently small, you can have regular solution, and so even if there is no proof in 3D, at least you can expect that you have as a final steady state the Bose-Einstein distribution without any condensed part. So at least this is a good model from this point of view. Take the mass which is small, then you can follow, it has a solution which is regular, and then you can do all the mathematics that you want. But this more or less is the result, sorry. Take the initial mass sufficiently small, and then take the L2 norm, which is this way, and then you obtain a uniform bound. As I said before, it's difficult to estimate the extra side of the mass. This is the first part of the story. And now, what happens when the mass is big? So when the mass is big, the first idea,
Can I see the previous one?
Yeah.
So, but if the mass is small, then it means that the smallest the mass, you can take the initial data larger in the L2 norm.
Yeah. You have a relationship, is very strange. But this is what you can construct, of course. What is more interesting is the second aspect of this equation. So let's check what happens to the second moment. For the standard Fokker-Planck equation, then this is controlled by the mass, and then minus 2 times the same quantity, and so the second moment cannot grow. It cannot go down. So you have here a relationship that says that more or less the second moment stays bounded. Yeah? But here you have additionally, you have minus twice, and then the fact that there is the presence of this square, you have v square f square here. Yeah? This gives you an idea. So this is the added part. Let us check what happens to this added part if I can control from below. And suppose that the solution remains regular, and look at what happens to this quantity. And so thinking about, I was able to derive this inequality that holds any time that the exponent p is bigger than 2 over the dimension of the space in which you are working for. And suppose that you want to bound from below v squared times f to the power p plus 1, then you find that this is bigger than a constant, then you have the mass, which is the mass of the problem, which is constant in time, and then below you have exactly the second moment. And what is essential is that you see that this is, you can obtain something from this, let's say a bound from below, any time that p is bigger than 2 over d. This is the case. But if we do, in our case, in Kaniadakis-Quarati model, p is equal to 1 and d is equal to 3. So you get essentially that v square f square is bounded from below by the mass to power phi over 2 times a constant times the second moment to 1/2. What means this? That, when the second moment is small, this became large. By the way, one can find an explicit constant for b. And if you consider the evolution of the second moment and you insert this lower bound, you see immediately what happens. Here you have the mass, which is a constant. This is a constant. Then you have the second moment. Here you have the second moment to 1/2. And then you are looking for the minimum value of this function. The minimum value is attained at this point. It's easy. And what you have, in this point, the value of the function phi is 6 times m minus something, which is related to a power of m which is bigger than 1. So here you have m to the power 1. Here you have m to the power 5 over 3. So it's enough to choose m sufficiently big, and then you get that the maximum is negative. In other words, if you suppose that the mass is sufficiently big, this function is less than delta, then you conclude with this contradiction that the second moment, which has to be bigger than 0, is the second moment initially minus delta t. And so if the initial mass is sufficiently large, you lose the second moment in finite time, but this is due to the fact that I was supposing the solution regular. So this is not the case, the solution is blowing up. And I get the same result, not only when the initial mass is sufficiently big, but even in a second case in which the second moment is sufficiently small. Let's say, if my gas has no enough energy initially, then the condensation wins. Which is expected, of course. Why this? Since in this case I can kill one piece and there is only this part. And if the second moment is small, I get that this quantity is strictly less than 0, independently of the value of the mass. So for any given mass I can find, so the second moment so small that it started to decrease, and so the second moment starts to be negative after a finite time. To end up, Kaniadakis-Quarati model has formation of singularity in two different situations. This is what I was able to prove with constants, but it simply means that the mass has to be bigger than something, or the second moment has to be smaller than something. In the case in which I'm looking at the second moment, which is smaller than for any fixed mass, I can find the second moment. Then the solution is blowing up in finite time. Unlikely this has been obtained by contradiction, and so I'm not able to quantify at which time this will happen. And second, and this would be more important, if the blow up really means condensation or not. Let's say if I'm waiting some time after the blow up, can I see some part of the mass which is concentrated on a delta? And this is one of the 100 problems which are open with this Kaniadakis-Quarati model. Second, I'm not. Okay. Since here there are few problems which are closed, so at least something is understood, or the mass is sufficiently small in a problem like this, and then you follow the solution remains regular, or you have enough mass initially above the critical mass, and then you have blow up in finite time, but no more than this can be said. So we started to think to a different problem, and the problem is different in this sense, that we still want to maintain the property that the steady states of the equation can have some condensed part. Let's say delta can appear, so the critical mass still exists. And this can be done with a different strategy. Let's say taking some sort of drift which is linear in a sense, and taking the diffusion which is sublinear. And as I said before, you take a function beta which is increasing and regular, let's say, and that is not growing more than to a certain level beta infinity. And here there is also a condition on beta prime that guarantees that you can get results. And then we did this in general, since in principle it was not difficult to study this sublinear diffusion. We started to think to what happens when you have a potential which is not with only one hole, but maybe with a lot of holes, with a lot of minimizers, to understand where the delta is forming, how many delta is forming in one set and in one other. So this is an interesting problem in itself. And so the condition we put on the that we took this strictly convex with a condition of this type that guarantees that more or less at infinity it behaves like e to the power 2, and so you have linearity outside of a certain bounded domain. This has been studied recently, and the main difference with respect to the Kaniadakis-Quarati model is that Now we are in dimension 1, we can have still a critical mass, and this is due to the degeneracy of diffusion. The fact that the diffusion is not able to act when the solution starts to increase after a certain level. And then, for this type of problem, due to the fact that it is in 1D, you can explicitly characterize the critical mass in terms of the diffusion and the confinement, but, as I said, there is a main difference, is that a problem like this with respect to the Kaniadakis-Quarati model, which is the toy model that really represents relaxation of a Bose-Einstein gas, here, the fact that you have a linear confinement does not allow a blow-up in finite time. You can think in this way. If you take this equation and you write down, consider V prime equal x, so take a linear drift, and study the evolution of the usual Boltzmann H function, f log f. Then from here you get something which is non-positive. From the linear drift, you have a growth which is linear. The mass is preserved, so at any time t, the integral of f log f cannot be bigger than the mass times the time t. And so at any time you have an upper bound for the Boltzmann H functional, so no blow up in finite time for a model like this. This is the reason behind. And so if you have not some condensed part initially, you cannot hope that this happens in finite time. What is nice is that this equation can be studied in such a way that you can put initially some condensed part somewhere, and then you can follow what happens to the condensed part, which clearly regularizes, and it moves towards the minimizer of the potential, and at the end you will find if you are above the critical mass. So, some mathematics that allows to prove everything. You know, everything for this problem is studied in the space of measures, yeah, and everything is split down in the absolutely continuous part and in the singular part. This is almost general, and you can easily define a notion of weak solution, and I set in red here the difference between the various pieces. Let's say this piece takes into account the wall measure. So you can follow the wall measure. Then there is a part in which it appears the derivative of the diffusion, in which only the regular part is present. So there aren't problems to study problems of this type, since you know the diffusion sees only the regular part. And if not, it will be a problem, since here you have a derivative with respect to x. So this is the main argument that says, so you see the wall measure here, and you see only the regular part here. This makes the problem handleable. And then, as usual, you can do almost in the same way, but there are technical problems that can be overcome. You introduce an entropy, which is given like in terms of the potential and in terms of the energy. And here, the density, you know, is given in terms of your function beta, which is sublinear, and in terms of another function which is written here, which is sublinear, still sublinear. So putting here together, all these quantities sublinear. In other words, it does not see the singular part of the solution. Even if the singular part is present, you see only the regular part of the solution. By the way, by this definition, you can define easily the value of the function E through this relationship, as usual. And then you can see that when you go to plus infinity, you have 0 in 0, and then the limit of the entropy is minus beta infinity. Here the definition of entropy, functional, and here there is the definition of entropy dissipation, functional. And also this is a definition in which when you take the dissipation relative to a measure, you see in beta there is only the regular part, and then here there is the singular part. So the dissipation can be defined also in this case in which we have measure, everything goes fine. And of course, the dissipation then one set infinity when you have not beta in W11. And what it can be proven is that even in this case, in which you have measured, you have an entropy dissipation inequality, or equality in this case, in which if you start with T0 and T1, at a subsequent time, the entropy is related to the previous one. This is diminishing, since you have the integral of a positive quantity. This is fairly standard when you have to do with a function. It's not so standard when you have to do with a measure. So this was the technical part of the proof. And if you use more or less the strategy which is you can find in this book, and one of the co-workers was one of the writers of this book. This explains why we were so good in obtaining the result, more or less. Then, you take a potential which is strictly convex, more or less. There exists a lower bound which is strictly bounded away from zero. This is the usual situation that you have to do. Then you take a measure with the second mass which is bounded. Then you can prove there exists a unique solution to the problem which satisfies the dissipation inequality, and the relaxation parameter is given by the lower bound lambda of the potential. But this is fairly standard, as I said. And then you can define a semigroup of continuous mass in such a way that when you take the Wasserstein metric of at any time with respect to different initial data, then it decays at the same, not at the rate 2 lambda, but at the rate lambda with respect to. And then you have also a principle that says that monotonicity principle, that if rho 0 is less or equal than eta 0, then you obtain the same at any time subsequent time t. This is due to the structure of the equation. So you have a notion of weak solution. You have convergence. More or less is written here. If you set the equilibrium here, then you have exponential convergence toward the equilibrium. And what is needed is how to characterize the steady states. And here, it depends on the function that you have. It seems I have time.
10 minutes, 15
Yeah.
minutes.
And so, sorry. And so let us consider the entropy functional, which you know a prime is increasing, so you can define the pseudo inverse, and then you can define u infinity alpha like the pseudo inverse evaluated in minus the potential minus alpha, and then you consider the strictly increasing function of alpha, which is defined in this way, the integral of u infinity to the power alpha in dx. And what follows is this one. If this function evaluated in 0 is less than 1, which corresponds to the fact that you are supercritical in this picture, so you have the mass which is above the critical mass, then the steady state has a regular part, and then there is a delta which is, let's say, a condensed part which is concentrated in 0. When you are exactly critical, then you have only the regular part, and then if you are subcritical, which corresponds to choose m0 bigger than 1, then you have the same property here, and then you have the characterization with the alpha star, which is the unique value of alpha that gives m of alpha equal to 1. So you have a complete characterization of the steady state. Of course, you can increase the difficulty of the problem by choosing the potential v of x, which has a certain number of points in which it attains the minimum. Instead of having only one minimum, you can also have a lot of minima, apart that it has to satisfy what is called a coercivity condition, which is written here. In this case, the minimizer can be characterized in this way. When you are below the critical mass, then you have a unique minimizer, which is in L1. And in this case, the minimizer is bounded, while when you are exactly with mass equal to the critical mass, the minimizer has a point in which it blows up. In all points in which you have the value which is the minima. So you have, at this point, when you are exactly with the mass equal to the critical mass, in all the minima of the potential, you are not finite. In a sense, it manifests the idea of the solution to blow up in this number of points. And when you are above the critical mass, then there is a non-trivial singular part, but it's impossible to identify. There is no unique minimizer. There is a unique minimizer only when there is a unique point in which you have the minimum of the potential. If not, it's difficult to understand which part of the mass goes in one minimum and which part of the mass goes in the other minimum. Unlikely. Yeah. And as I said before, any time that you have the function beta, any time that you have the function v, then you can identify easily the critical mass of your problem. Last, also in this case, we can apply the general strategy, which is outlined in the book by Ambrosio, Gilli, and Savary, and to see that the entropy decays at a power 2 lambda, and then this implies that the Wasserstein metric decays at a power lambda. Yeah? This is well known. So this gives, so we have decay towards the steady state. The problem is that we don't know exactly which one of the steady state will be achieved, which part of the delta is in one minimum point on the other when the minimum is not unique. Yeah? This is what we did on this, I think, nice problem, but you know, the part of problems that are closed are really few with respect to what has to be proven. So, for example, take the Kaniadakis-Corati model to speak about one classic problem which is completely open. What happens to the large time behavior, even in dimension 1? Sorry. Here you have to choose dimension 3, if not in dimension 1 there is no formation of singularity. I will be back to this problem in a minute. Then, and this will be maybe the most interesting part, both from a mathematical point of view, a physical point of view, take the mass sufficiently large, then you know that in finite time there is blow up. What happens after? Maybe, I don't know which type of methodology can be used for something like this, but it would be really nice to understand if after a certain time there is some part of the mass which is localized in 0. And then, starting to the problem 1D, the Nash type inequality I proved to control the L2 norm fails if you take a 1D problem with a nonlinear drift in which the power 1 plus f to the n is such that n is bigger or equal than 4. Apparently, when you increase the strongness of the drift, it's still impossible to prove regularity even for small mass. Maybe this is done to the fact that I used an inequality which is not the right one, but in any case it's interesting. So up to a certain point, the linear diffusion is able to control the regularity when the mass is small. But what happens when the drift is so strong that apparently the linear diffusion is not able? At least this is completely, in a sense it means that when n is bigger or equal than 4, at time 0 plus, immediately it appears condensation. Who knows? This is complete. And also in this case, in 1D, for n less or equal than 4 but bigger than 2, in which we know that there exists a condensed part, what happens? There is exponential convergence to equilibrium for the Kaniadakis-Corati model, like, let's say, in 1D with a strong linear drift or not. This is exactly what we started to do with Naufel, but still we started, but we are not arrived. I think I can stop here.
Very nice talk and a nice way to end the day. Probably some questions. Time for questions. Yes, please.
Do you know in which kind of limit do you expect to obtain this equation for as an approximation for the Bose-Einstein condensation? Because in the papers of Semikov-Tachev and all these papers in the physical literature, they seem to assume that in all the cases they have to use the kinetic equation. I mean, this Welle-Uhlenbeck equation, or you call it Boltzmann-Nordheim or something like that.
I can say that, what is known now, the picture is this one. Take the linear Boltzmann equation, let's say the elastic particles in a background, and then take a singular kernel, and then switch collision in a grazing collision setting. So this gives you Fokker-Planck. So if you take a nonlinear model, it gives Landau Fokker-Planck. This is part of the work where you say Drake-Villani. No? But if you take the Fokker-Planck equation, if you take the linear Boltzmann equation, then you fall into Fokker-Planck. Then think this is relaxation of a gas of elastic particles in a medium. Then take a Bose-Einstein gas relaxing in a medium. Then you get this equation.
But you need singular kernels or something like that. Singular kernels or something.
In a singular kernel, you need a singular kernel. You need a singular kernel. This is the picture. For the Fokker-Planck equation, it's not for the Bose-Einstein particle, it's not written. I think for Fermi-Dirac particle is something that is part of the thesis of Vauchelet. I remember. That was a student of Naufel. By the way, this is a model that simply it gives a picture of relaxation of a gas, and then it has been derived by phenomenological observation by Kaniadakis and Quarati. They were motivated by a completely different approach.
The point that I noticed in the physical literature, and I think that in the case of Spohn probably is insisting in the same. I mean, all these physical papers, that normally the kernels that the physicists use used to be constant for small energies. Yeah. And then you cannot get this kind of Fokker-Planck equation.
Exactly. You need a singular kernel.
You don't have any small parameter at all, and you cannot simplify it at the Fokker-Planck equation. And then, I mean, maybe there is a physical situation where this kind of thing could arise. No?
This is, now it's questioning if this equation is too physical or is not physical at all. But in any case, if you want to pass from Boltzmann to Fokker-Planck, you need a singular kernel.
Yeah. No, but the point is that the situation is very different in Compagnies, because in Compagnies...
Yeah, exactly, this is different.
But in Compagnies there is a true small parameter. There is a true small parameter because the interaction, in Compagnies describes photons, and these photons are interacting with matter, and then there is a small number there, and then you can derive a Fokker-Planck equation.
I agree completely. But then,
I'm going to ask, Peter's got a question, he's been very patient.
Thank you. Just a very general comment. I mean, these equations are also the quantum Boltzmann equation and the bosonic framework can only be seen as a model for the development of the Bose-Einstein condensate. That is, for what happens before the condensation process. If then you want, and here's an interesting mathematical problem. If you want to sort of model pre-condensation process plus what happens after condensation, then you would have to couple one of those equations of quantum Boltzmann to the full quantistic Schrödinger description, and that would be very interesting. It's something that we actually looked at briefly with Lorenzo and Reto Barber. Honestly, we didn't get very far. There have been some subsequent works on that, mathematical works, but nothing really, that solves the problem. And this is really a wide open problem, which I consider extremely challenging.
I'm not an expert in any of this. This question will make that really clear. But you obviously you have this nice result of the blow up in finite time, but you could not say whether that blow up was associated with or led to condensation. I mean, is it true that, can you say anything about the nature of the blow up, and would that be related to give you any insight into the condensation, or is this a stupid question? Profile of the blow up. So my question. But the profile. So I have two questions. Can you, with these methods, imagine that you would get any information about the profile of the blow up, even though you cannot say when it happens?
It's difficult. Yeah. So from the mathematical point of view, you can say something, then you try with a numerical method, and then you see simply that the solution is blowing up, and you don't know what happens after. There is some math which is considered. So the notion of what happens after the blow up, to understand, it's a very difficult question.
If I remember correctly, our computations with Lorenzo were completely unconclusive on whether
Inconclusive.
Inconclusive on whether and how whether it happens even in finite time or whether and how the blow up happens. I mean,
Well, of course, numerically it's pretty difficult to estimate.
Yeah.
exactly.
If we have to make a guess, was finite time.
Exactly.
But,
We have to make a guess. But,
yeah, but
I wouldn't bet on it.
One of the things you said was that even when you have small mass, if these,
Can you repeat?
one of the things which you have said, even when you have small mass,
Yeah.
if the L2 norm is very small, you still get blow up. So in order to
Not that two norm, the second norm.
the second norm. Sorry,
norm.
was small.
The second norm.
Sorry. But that means, I mean, in this case, the steady state should be regular, right? So if you would want still to go to the steady state, you would have to get out mass
Yeah.
from the concentration again, right?
So it's a strange situation. Apparently, if you take second norm, which is small, so the gas has no energy at all. It's a really small gas, so the temperature is really low. Let's say in this way. Then the nonlinear drift does not allow diffusion to do something. Apparently, everything is condensating. So I don't know either if you find that the solution will converge to the Bose-Einstein distribution in this case, or there is something which is formed. It's a strange equation. As soon as you have blow up, you cannot follow regularity. You don't know what happens. I have no idea. Yeah.
Anything similar known about self-similar solutions near blow up, like in nonlinear optics?
But for this equation, it's not easy to find self-similar solution. I tried, of course. This was the first. Yeah. When the nonlinearity is in the drift, let's say, is a new question. Usually, we know a lot on nonlinear diffusion. We worked in the last 10 years on that, but not when the diffusion is linear and the nonlinearity is in the drift. So you lose the structure of gradient flow, you lose a lot of things. By the way, the physical problem is this one.
In Companellos, it's possible to compute the profile. I mean, in Companellos, the profile was computed, and it's because everything is dominated by the drift term. The diffusive term doesn't count, and this equation looks more singular.
I agree. It's not the same, but it's same.
So, well, look, I think that Giuseppe has more than earned his glass of wine in the reception. I think it's been a really nice talk on what seemed to me very nice recent work, and thank you for explaining it so well for us.
Thank you.
Thank you, Giuseppe.